Thank you for the introduction. Thank you everybody for coming. I'm not sure this is working, so I just have to check my voice maybe. We'll see. Right. So, I'm based in the School of Civil Engineering in Leeds, and my general PhD question is, how does turbulence influence structure? How does it flow around a structure? Such as this bridge cable structure here. This was a bridge cable collapse where there was a failure due to the oscillation. It's not quite as glamorous as the Tacoma Narrows Bridge, but regardless. And today I'll talk about how can we simulate this in our CFD model. So first off, we'll be looking at, if we want to study the flow past a cylinder, we could look at different effects, maybe a rigid cylinder or some straight suppression, vortex suppression devices onto the cylinder, or also fluid structure interaction. But to take it back one step, I'll be using OpenFOAM here and modelling with large eddy simulation. So I'm resolving the larger scales, I'm modelling the smaller scales. And how can we prescribe this turbulence at the inlet? Because with the papers, when I was trying to validate my numerical model, the papers all define the inlet using just a smooth inlet with maybe some turbulent kinetic energy, but the authors noted that this will quickly die out. But that's what they expected. So we need to create some turbulent inflow, and there are generally two methods to do this. We could use a precursor simulation. This could come from a CFD simulation, or it could also be from an experiment. And this is real turbulence, or as real as we believe it to be. There are some problems with storage if you want to store every time step, of course. Or we could use a synthetic method which creates the turbulence, this turbulence in situ in our domain. The problem is you might have some missing inflow. You might not know exactly how your turbulence should look like at the inlet. So the first thing I'll talk about is grid turbulence. So how can we use a grid turbulence precursor to kick off our simulation? And briefly on grid turbulence, we pass a uniform flow through a grid, and we have two regions, a regions of production of turbulence near the grid, and a region of decay, which becomes universal as we increase our downstream position. We could simulate the full grid itself upstream of our geometry. That would be a rather brute force approach. So instead, I opted for the projected inlet method of Blackmore et al. And you project whatever grid geometry you want onto your inlet, and you set your inlet velocity to be 0 at the bars, the blockages, and non-zero in the gaps where you produce the jets. And the general picture we get is, so here we have vorticity magnitude, and we have jets coming from the gaps, and they eventually break up, and we get something which looks reasonably homogeneous, isotropic. Around about here, we'll say 2 channel widths downstream. We can also look to wind tunnel experiments, which have utilised multi-scale geometries, multi-scale and fractal geometries as well. And we can compare using the same solidarity across the grids of 44% and the same inlet velocity. We can try and gauge which grid might be better if you're trying to design a grid turbulence experiment or a simulation. And the fractal design really boomed about 10 years ago. Oh, here we go. Really came into focus 10 years ago by a number of researchers at Imperial who were looking into fractal generated turbulence. And many applications, many different reasons we'd want to use grid turbulence and fractal turbulence. And for the keen readers, I'd refer them to this paper here, or this book even. So the fractal design I've used is actually, it was used here in this wind tunnel experiment of Hurst and Lavoie, and we have a cross combined with a square fractal design. And they reported poor homogeneity because I think there are two main reasons. One of them is that their space filling parameter wasn't quite big enough, which is how far your grid expands out. And also the large cross in the middle seemed to generate some very, I think 15 integral length scales downstream. They could still see the wind shadow off of this cross. So I tried to design what might be a more suitable grid and produce better homogeneity. And by combining two fractal grids here, left and right, plus the cross here on the right, which means that there's an obstruction behind the center line for each of the four grids, we can sort of push the solidarity out, and hopefully the jets, which are persistent in the corners, will be broken up by smaller bars up here. If we take a snapshot of velocity, this is velocity one channel width downstream, so quite close to the grid, near grid. We see the regular and the fractals still show some wind shadow, whereas the C fractal seems to, the jets have been completely destroyed by one another. And if we look further downstream, the problem I've seen with the fractal and the cross design is that once the turbulence seems to decay, your mean flow persists. So you can have a problem here where you've got this well-defined cross. This is less obvious with the C fractal. Still slight jets, but it's less obvious. It's much improved. So if we look at our integral length scale by integrating our correlation function, I was finding with the regular and the multi-scale grid that I was getting two well-defined signals. This isn't quite as nice as Angela's drop-off of F, but if we integrate these two lines, if we separate them and integrate them to the first crossing point, we'll get an integral length scale for the faint line, which is roughly double that of the dominant line here, signal. And this is for the regular grid, quite close to the outlet as well. And once we plot these up for all four grids at various downstream positions, with the regular and the multi-scale grid, we have quite large integral length scales. If we just consider the dominant signals, we get quite nice agreement. They're all around, this should be in millimeters, around 10 millimeters for the four grids. But these larger structures persist in the regular and the multi-scale grid, whereas with the faint signals for the fractal grids, it's a lot less, they're smaller structures. So any large structures generated in the fractal cases seem to be broken up by smaller bars. And if we can introduce a passive scalar into the simulation, which is just solving a transport equation for a passive scalar psi, and I found especially with a regular grid, we actually get patches of, when the jets emanate from the grid, we get some patches, we get some clumping of the dye, which is completely undesirable if you were to design a combustion device. You don't want clumping of some species. So if you look very close to the grid, again, we get, so if you let this evolve for longer, they all look alike. You can't really distinguish between them. But for the regular grid, these jets, these inlet jets, aren't broken up fast enough. So we see a bit of clumping, and this is only after a tenth of a second. With the C fractal grid, and with the multi-scale and the fractal grid, actually, there's less clumping, certainly with the dye, this passive scalar. Some conclusions. If you design a fractal grid and you put in a large cross, that can dominate the flow far downstream and lead to inhomogeneities. So the jet breakup is more immediate behind the combined fractal grid, and there's less clumping with the fractal and multi-scale grid compared to the regular grid. And these simulations, if you take a slice, can be fed into a synthetic eddy method, for example, and used to generate, if you have a library of turbulence, you can pop this into your SEM and kick off a simulation just from that. Okay. And thanks to my EPSRC and my supervisors as well.
Can you give us more detail about your simulations? The Reynolds number and which, I guess you mentioned for the passive scalar open form, so I guess you did your simulation with open form.
Yes, so the Reynolds number, the grid, you can either define your Reynolds number off of the grid,
yes,
or a local Reynolds number, which might be defined on your Taylor microscale. My grid Reynolds number was quite similar for my multiscale fractal and combined fractal. It was slightly larger for my regular grid because it's based on the largest bar width. But they all seem to asymptote towards a local Reynolds number of about 100 or 150 downstream. Yeah, off the Taylor microscale.
And your simulation are DNS type?
No, this is LES.
LES?
Yes.
So which model did you use for?
With dynamic K equation. So there's no assumption between subgrid scale energy production and dissipation. And it allows for backscatter as well.
Okay, thank you.
Questions? There's nothing to stop you doing active grids as well, is there, with your flow condition? You can move the
One thing I could do is pulse the inlet. Oh, without moving the grid, yeah. Oh, I could move the grid possibly, or yeah, I think possibly what could be quite interesting is just to pulse the inflow, which would be a quite easy thing to do.
Okay, very quick.
Yes, how many cells do your simulation have, and how long does it take to run each of these simulations?
These simulations they're around about 22 million cells, and on 96 processors cores, that takes it's a couple of weeks usually to get things. Yeah.
So as you might know that in turbulent flow, if you add a small amount of polymer, it can lead to huge reduction in skin friction and and this reduced skin friction can cause lower pumping cost, which leads to low energy savings. Not only polymers, but some micelle forming surfactants can also cause drag reduction. So the examples of application of drag reduction due to polymer addition is in Alaska pipeline and in the fracking process. So next comes the concept of maximum drag reduction asymptote. So we might know that if we add polymer in the turbulent flow, it leads to reduction in skin friction, but there is an upper limit to this reduction, which is given by maximum drag reduction asymptote. And this asymptote is independent of molecular weight, concentration, or chemical structure of the polymers. So to further understand this, we can see the velocity profile plot of stringwise velocity versus wall normal distance. Here the red line shows the Newtonian wall law without addition of any polymers, and the blue line shows the work profile or the MDR profile with addition of polymers. So when we add the polymers in the turbulent flow, the red line shifts towards the blue line, and that's the upper limit of the drag reduction. So what in recent literature it has been found that even in Newtonian turbulence there are moments of low drag when the velocity profile approaches the maximum drag reduction profile. And these moments are called as hibernating turbulence. So till now it has been observed for Reynolds number, which is based on U tau and channel half height between 70 and 100 for Newtonian flows. So this is a work which is done by Lee et al., where they have shown that for RET of 85, if we see the lower plot, this is an instantaneous plot of wall shear stress and log loss slope. In the lower plot, it is the instantaneous wall shear rate. If you see that whenever there is a decrease in wall shear rate from the mean, there is an increase in log loss law from 2.5 to 11.7, where 2.5 represents for Newtonian wall law and 11.7 represents for MDR asymptote. So we can see that whenever there are moments of low drag, there is a jump in log loss law. So from there, we got motivation to further investigate this phenomena for Newtonian turbulence with using experiments. So we are doing an experimental investigation of this phenomena in a large-scale channel flow facility, which has an aspect ratio of about 12, and fully developed flow is ensured by keeping length to half height ratio of 596. Just to emphasize again that we are doing all our experiment without addition of any polymers, and we are trying to see these moments of low drag. So for measurement techniques, as I said before, that we need simultaneous measurement of wall shear stress and velocity. So what we are doing is we are using glue-on hot film probe anemometry for the measurement of instantaneous wall shear rate, and at the same time we are doing velocity measurement directly above the glue-on probe for the velocity profile measurement. And we are also doing pressure drop measurements for calibration of our hot film probes. So as we know, these low drag events or the hibernating turbulence are the events of low drag when the velocity profile approaches the maximum drag reduction profile. So it is quite ambiguous in terms of the criteria. So before in the literature we found two papers who has done this work by Kushwaha et al. And Wali et al. Where they have used the threshold for reduction in skin friction to be 90% of the mean wall shear stress. And the time duration of this low drag event is given by non-dimensional time duration T star, which should be greater than 3. So we did our experiment at R eta of 100, and this is a plot of normalized wall shear stress versus time. Here T star is a non-dimensional time, which is non-dimensionalized by u tau and h. So here we can see that the T star of 0, the normalized instantaneous wall shear stress goes 90% of the mean, and stays there till T star of 4, which is always below 90% of the mean. So this can be called as a moment of hibernation or low drag event, because the normalized wall shear stress is going below 90% of the mean. So what we do is, for each Reynolds number, we do our experiment for a really long time in the order of few hours, so that we can collect lots of moments of this hibernation. So this instantaneous plots of wall shear stress is at R eta of 84. Here the gray line shows the instantaneous wall shear stress for low drag events, and then we combine together all those events. So the T star of 0 marks the beginning of hibernation, and then we do ensemble average of all those instantaneous wall shear stress, which is given by black thick lines. So till now we have done our experiments for 3 Reynolds numbers, 67, 84 and 103. And first plot shows the normalized wall shear stress, which has been ensemble averaged over all the low drag events versus T star. Here we can see that for all these 3 Reynolds number, there is although our condition for hibernation criteria is that it should be 90% of the mean, but what we observed that it is always close to 60 to 70% of the mean during these low drag events for all these 3 Reynolds number. But what we found difference is the fraction of time which is spent in this hibernation or the low drag events. So when the Reynolds number was 67, we could get almost 1.8% of time which was spent in hibernation, which decreased to 0.2% for R eta of 103. So yeah, so as I told before, we do simultaneous measurement of wall shear stress and velocity. So what we do next is, when we get the moments of low drag event, we collect all those moments and recalculate our new u tau based on those low drag events, and then we renormalize our velocity and y plus. And then in this plot, the open symbol shows the long time average velocity profile, and the closed symbol shows the velocity profile during the moment of hibernation. So you can see that there is an increase in velocity u plus for all the moments of hibernation. So we did for 2 wall normal distances for each Reynolds number. So there are 6 plots which is for 2 for each Reynolds number, which is given by triangle, a square, and the circle symbol. We see that for all R eta of 67, 84, and 103, there is an increase in u plus during the moments of hibernation, which further verify the phenomena of hibernating turbulence. Then we also, as I said before, that we have to use 2 criteria, that T star, which is the minimum time duration, should be greater than 3, and the threshold should be 90% of the mean. So then we try to change this criteria and see how it affects the moments of hibernation. So this plot shows the frequency of hibernating event per unit hour versus minimum time duration. So before it was T star of 3, then we kept it between 2 to 4, and we saw that there is an exponential decrease in the moments of hibernating events. And then we also changed the threshold value. Before it was 90% of the mean, and then we kept it from 75 to 95. And we see that again there is an exponential relationship between number of events and the threshold value. So finally, the conclusion of this work is that we found experimental identification of hibernating turbulence for all these 3 Reynolds numbers, 67, 84, and 103. And we see that the conditionally sampled streamwise velocity profile approaches the works MDR. And we see that the hibernating events reduces with increasing Reynolds number. And we also see that we can change the criteria for hibernation to further increase or decrease the number of hibernating events, changing both minimum time duration and threshold. But there are still many open questions in this work, that what happens to the hibernating events for higher Reynolds number, R eta of more than 100, which we are still trying to do. And the second is how the Reynolds stress behaves during hibernation. Thank you.
When the metals is
Yeah. No, it's a local measurement of wall shear stress using glue-on hot film probes. Till now, we have been able to do using only one glue-on hot film probe, so we have not done any special measurement like using many hot film probes so that we can have some kind of special information. So till now, we just know about the at one location.
Do you know what the resolution of your probe is in plus units? How big is the
It's in
sensor?
plus units of about 10, order
10.
of 10.
So what's the difference between a hibernating event and a low-speed streak? Low-speed
Because
streak
still there, but low speed streaks has, because we still get RMS value of shear stress, which is not that observed in the low speed streaks. So even if the RMS we see during low drag events, so RMS value does not decrease that much. Only it's not a laminar patch, it's still turbulent flow, because we see all the spectra, broadband spectra, and the fluctuations in U and the tau. So it's not low, we cannot call it a laminar patch, it's more like just that the amplitude of fluctuation is reducing for those moments.
Hi everyone, so I'm Jacob and I'm going to talk to you today about my research project, which is on experimental and numerical modelling of aerated flows over steppe spillways. So steppe spillways are a very common overflow design for reservoirs because they're relatively easy to construct. They dissipate large amounts of energy to prevent scour at the foot of the dam, and they also aerate the flow, which can help to protect the spillway surface. And a lot of new reservoirs get constructed using concrete steppe spillways. But also, there are a lot of very old masonry steppe spillways, like the photograph on the left, especially in the UK. And I think the average age of these spillways is over 100 years old. So part of my project is looking at trying to use CFD modelling to see if we can predict the important flow features in steppe spillways, but especially in the aerated region, to help with the design of new steppe spillways, but also for the maintenance of these older steppe spillways. So when we get high flows over a steppe spillway, you get what's called skimming flow, where the majority of the flow skims over the steppes in a coherent stream, and then in the steppe cavities, recirculating vortices form. At the crest of the spillway, a turbulent boundary layer forms and increases in depth until it reaches the free surface. And this is known as the inception point. And this is where aeration begins as turbulence to the free surface draws air into the flow. And this air is then transported throughout the flow and into the steppe cavities. And it's important because it can affect the pressures in the spillway, which can help protect the spillway surface, especially in masonry spillways. But it also increases the depth of flow, which is important for the design of the spillway sidewalls. And these are the two multi-phase CFD models I've been using. The first is the volume of fluid, or the VOF model. And in this model, a single momentum equation is solved for the two phases. So you can't get a relative velocity between the phases, so you can't get dispersion of one phase within another, so therefore air entrainment can't be predicted. Whereas the next one is the Eulerian multi-phase model, and in this one, a momentum equation is solved for each phase, so you can get relative velocities, and therefore you can get dispersion and air entrainment being predicted. The video's a little bit slow, but this is, I've modelled two steppe spillways. This is the first one I've modelled, which is at the LNEC in Lisbon. It's a metre wide and consists of 33 steps, which are 80 mil tall by 60 mil long. And we've got some air volume fraction contours from the CFD models. So on the left, we've got the VOF model, and as would be expected, we don't see any air entrainment. But on the right-hand side, we've got the Eulerian model, and we can see that we do get air entrainment, and we've got this downstream region where there's high amounts of air entrainment, and upstream, especially in the steppe cavities, we don't see the air entrainment. But what you do see is that the inception point of air entrainment in the Eulerian model appears to be close to the crest of the spillway, which isn't actually the case in the experiment. So even though the Eulerian model is predicting the air entrainment, it does seem to be predicting the onset of it slightly too far upstream. Okay, so here's some velocity profiles at different steps moving down the spillway. And I've got the Eulerian model and the VOF model, both in conjunction with the realizable K epsilon turbulence model and the SST K omega turbulence model. And you can see that in the upstream part of the spillway, it seems like all the models are predicting the velocity profiles pretty well. But as you move further downstream, it only seems to both the Eulerian and the VOF model predict the velocities well, but only with the SST K omega model. And it's also noticeable that with this model, with this turbulence model, the VOF model only predicts the velocities accurately up to a certain depth, and this is because it doesn't predict air entrainment, so it's underestimating the flow depth in the aerated region in the downstream part of the spillway. Next, we've got the air volume fraction profiles, and the VOF model doesn't predict that. This is in the aerated region only now. The VOF model doesn't predict them accurately at all, as we'd expect, because it doesn't predict air entrainment. We can see that the Eulerian model does predict them pretty well, especially again with the SST K-omega turbulence model. And then next we've got some free surface profiles. Here in the experimental data, the inception point is at around 1,500 millimeters on the x-axis. And you can see that after this point, the Eulerian model, again with the SST K-omega model, predicts the free surface really well. But upstream at this point, it slightly overpredicts it, and this is again because of this, because it predicts the inception point of air entrainment slightly too far upstream, but downstream of the inception point, it predicts the free surface really well. And the VOF model with the realizable Kepler model predicts the free surface reasonably well in the non-aerated region. So I'm quite happy with these results. I've managed to predict the velocities, air volume fractions, and flow depths in the aerated region reasonably well, which is something that hasn't been done before. So the next spillway that I modelled is one that we designed for the University of Leeds. Again, the video is really slow. It's relatively narrow, 150 millimeters wide, and it consists of 15 80 by 80 millimeter steps. And you can kind of see, even though the video is slow, the non-aerated region, the inception point, and the aerated region. And we've taken pressure measurements at steps 2, 5, and 12. And at these steps, these are the positions we've taken our pressure measurements on both step faces, and at the center line, and also at the wall. Right, so in this video, it's a bit slow, but I don't know if you can see, there's some dye being injected into one of the step cavities. And the dye seems to be restricted to 1/2 of the spillway of the channel width, but it also seems to circulate in an anti-clockwise direction. And what you actually see that at each step, there are 2 vortices, which I've named cross-stream vortices to distinguish them from the recirculating vortices I talked about before, going in opposite directions and meeting at the center line. But what's unusual is that the direction of circulation of these vortices changes at each consecutive step. So one step will look like the top photograph, where the cross-stream vortices impinge on the horizontal step face at the center line of the spillway. But then the next step will look like the bottom photograph, where they impinge on the horizontal step face at the wall. So this is quite interesting, but it wasn't expected, and it's a bit unusual. Again, so some air volume fraction contours for this spillway, and we see the same thing where the VOF model doesn't predict air entrainment, whereas the Eulerian model does, but again, it predicts the inception point slightly too far upstream. Okay, and these are the expected pressure distributions we expect to see in a step. So we get low pressures at the top of the vertical step face, but then on the horizontal step face, we get the highest pressures at the downstream end and the lower pressures at the upstream end. Okay, so here's some experimental and CFD pressure data from the spillway. So on the left-hand side, we've got the pressures close to the wall, and on the right-hand side, we've got the pressures at the center line. And this is at step 2, where the cross-stream vortices impinge on the horizontal step face at the wall. And it's at the wall that we see this expected pressure profile with the higher pressures at the downstream end of the step. At the center line, though, where the cross-stream vortices flow away from the step, we don't see this expected pressure profile, and there's actually very little variation in the pressure across the length of the step. And then we move to step 5. Now the cross-stream vortices are impinging on the horizontal step face at the center line, and it's at the center line that we see the expected pressure profile, whereas now at the wall, we don't quite see that same pressure profile. And then again, at step 12, the cross-stream vortices are going in the same direction as at step 2. And again, like step 2, we see the expected pressure profile at the wall, but we don't see much variation in the pressure at the center line. So this is showing that these cross-stream vortices are actually significantly affecting the pressure across the channel width. So it's something that in both the experiments and in the CFD data, so it's something that needs to be taken into account if we're going to design step spillways of a similar geometry to this. And you can see this in the pressure contours in both the VOF and the Eulerian models, that you get the high and low pressures both concentrated either at the wall or the center line, and this swaps at each consecutive step. And these are just some streamlines to show you the shape of these cross-stream vortices. So when we first saw this, we thought that maybe these vortices were due to the relatively narrow channel width. So I've run a lot of simulations with different width channels. So this is double the width. And you can see that instead of, well, now we get the pattern of cross-stream vortices is now repeated. So we've got 4 cross-stream vortices instead of 2. And I've tried this with so this is with normal wall boundary conditions, but I've tried it with symmetry planes and periodic boundary conditions to see if it was wall effects, and you get the same thing. And I've tried multiple different widths of channel, up to a 2 meter wide channel, and you can see that we get this repeated pattern all the way across the channel. So this is something we've investigated with CFD. Obviously, it'd be more difficult but interesting to do experimentally. We have superimposed some smaller steps into the spillway to double the ratio of step height to channel width, and you do see this pattern of 4 vortices across the channel width, but it'd be interesting to see what would happen if we could extend the experiment out a bit further. But yeah, so to conclude, I've used different combinations of multi-phase and turbulence models to try and predict pressures, velocities, air volume fractions, and free surface depths in step spillways. And I've been able to predict the velocities, the air volume fractions, and the free surface depths well using in the aerated region, using the Eulerian multi-phase model in combination with the SST K omega model. And also then in this other spillway, we've got this unusual pattern of vortices that seems to repeat itself as we increase the width of the channel. Yeah, and that's everything from me. So thanks.
Time for questions.
Hi.
What made you decide using the volume of fluid and the Eulerian models? Yeah.
Instead of, well, it's just, well, the volume fluid model is used quite a lot for free surface modelling, and a lot of what's out there so far looking at modelling step spillways is they only model the non-aerated region and using the VOF model, and they've got quite good predictions made in that area. So I kind of thought I'd use that as a little bit of a benchmark because it's been used quite a lot before. The Eulerian model, when I was just researching, when I first started, I was researching different multi-phase models. It was one of the ones that came up, and to be honest, I was quite surprised that people hadn't tried to use it before because it seemed like it'd be quite a good fit, and yeah, it was quite a good fit. So, yeah.
I've seen people using SPH.
Tried to use SPH for it, but the software that we would be able to use, the boundary conditions were too difficult, and you end up getting, you had to use periodic boundary, and it was just accelerating the flow, and it was a bit difficult to use.
Okay. Thanks.
Just wondering what sets your pattern? Is it the geometry of the steps?
Sorry?
What you see here is that set by the geometry of the steps, and can you do something to kind of try and excite something else?
Yeah, well, so I've looked at different angles, slope angles, and when you get a much shallower angle or a much steeper angle, you don't seem to get it as much. But when you don't change the angle much, you still seem to. It's not quite as strong, this pattern of vortices, but you still tend to see it. But strangely, with the geometry that I've got, when you make it wider, you get the repeated pattern. When I change the angle with the same width I've got, you get the repeated pattern. But then if you make that wider, you don't. So I'm not really sure why.
So I'll be talking about something strange. So you may not heard about this, something like a species sage. So I try to explain what they are, and then we like to investigate the characteristics in the stopping jet, which is a little bit non-conventional. So two combinations, species age and stopping jet. So I like this conference. 2 years ago, we presented this one. So we performed direct numerical simulation of a stopping jet at Reynolds number 7,000. And then this is how it looked like. So firstly, we established a steady-state turbulent jet, and then simply we stopped. And then this is the velocity profile along the streamwide velocity. Then we try to characterize the velocities, especially the center line velocity is the key point to understand the whole velocity flow field. And then there are a couple of lines. The black line is the steady-state velocity along the center line. So we typically know that it decreases as 1 over x. X is the downstream distance. And the red color represents the instantaneous velocity. So when t equals to 0, we stop the velocity. So you can see that the decrease of the red colors. And then the black color, which will be as dotted here. So we develop a model that it will be fitting into this behavior. So the center line velocity will increase over x, which is very strange, but you'll see how it looks like. And then inverse of time. And then if I plot, you can see the decrease the velocity, the dashed line doesn't work at the beginning, but you can see that after a certain transient time, it starts to work, and it's quite interestingly, this black line also proportional to x. Of course, it decreasing over time, but quite interesting that it's linearly increasing with the x. So we have done this study 2 years ago, and then quite successful. Now we want to apply the similar thing into the two-passive scalar, which is very relevant to combustion. So in combustion, typically we have a multiple species, typically the fuel and oxidizer. So one of the most important parameters is the mass fraction of fuel. That's one thing. And then second thing, I'd like to introduce a species age of fuel. So how we define? So mass fraction, I guess, quite straightforward. It's how much the species in terms of mass. And then typically, there's something called the stoichiometric ratio, which is very important in the combustion area. In terms of equation, this is supposed to be a vector line. So the left-hand side is the convective operator, and then right-hand side is diffusion. So I guess this is maybe quite straightforward in terms of mass fraction. This is quite interesting, species age. So what do you mean by species age? Basically, how much time it has spent in the region of interest. So for example, in combustion, basically, we have to have some chemistry, which is a time-dependent process. That's why time becomes important. So as a common equation, let's have some simple cases when everything consists of fuel. So the mass fraction of fuel is 1. This is a quite simple equation. You can see that the left-hand side is a material derivative, and then anything inside the domain getting old by 1. So as time goes by, things getting old or aged or aged. But this is the case of the kind of single species case. In the multiple species, then what we need to do is multiply by the mass fraction on the left-hand side as well as the right-hand side. So for example, if the mass fraction is every 1, then you can have the straightforward, things are getting old. And then if has some multiple species, then different species getting old at different rates. So it's basically proportional to the mass fraction. So actually, there is a rigorous derivation done by this paper. So this is species age, and then actually it turned out we also need the diffusion term due to the Brownian motion. So how does it look like in the turbulent jet? So this is a steady state simulation showing we call as a mass weighted species age because it's multiplied by the mass fraction. So this is a jet inlet, and then something you can think of it as far away from the inlet, things should be older, right? So in this color scheme, you can see that this is almost 0 over there, and then things are getting old around some number higher than the inlet case. And then one thing I need to emphasize is that it's not simply species age, it's also mass weighted species age. So I could plot the species age only, but things are a little bit more complicated. So I like to, actually this has a better mathematical property. That's why we like to use the mass weighted species. One interesting fact is that the fuel is only injected from the inlet, and then rest of the region is actually oxidizer or air. So over that region, so hypothetically, the age of the fuel can be very high, infinity, because this is a stagnant flow. If somehow the fuel is trapped into this region, it will be just stay there forever. However, because we multiply by the mass fraction, whether the fuel is almost 0 there, that's why we able to kind of make things 0 and in the ambient, and then because most of the interest it will all belong to this turbulent jet area. So mass weighted species has a better property than species age only, and then this is how it look like for a steady state case. So in turbulence, things we need to consider, this is kind of new variable. Some things we need to check that whether things are stationary. So I chose 2 points over there, and then I plot the instantaneous value over the time, and then things are stationary. So this is very good property of the species age. So what we want to do is that we like to model the stopping jet case for both mass fraction and mass weighted species age. And then this is how we look like. This is mass fraction, and then this is species age. So quite interesting, one thing you find from the mass species age, this area is almost remain red color. So even though time is changing, let me play again. It's quite so. For example, mass fraction, things getting diluted. If you remember, it has quite black color, and then things are very dispersive. But mass weighted species age has a kind of still seems to be a similar number after 70 tau. And then actually you can find more video on YouTube. So search DNS of Sa-Kyung-jae. You can see more video about this one. So for steady state case, which is quite well known, that it's well known that if you parameterize, if you do the scaling properly, R over X, and then the mean value divided by the centerline value, it has a self-similar behavior. So in terms of the mass fraction, has a nice kind of shape over there. And then the mass weighted species age has also the similar property as a self-similarity. And then when we try to extend to the unsteady case, there's several work about the the unsteady cases. And then they typically assume some self-similarity, which was not proved before that. So we have DNA data set. We can actually check whether they remain self-similar or not. Okay, so this is the same profile, kind of normalized profile, R over X, and then the value divided by the centerline value. Only difference is that this is the instantaneous value. And then there are a couple of lines. The blue one is a steady state profile, both of them. And the red one will be the instantaneous one. And then the cyan color is what you think is a new self-similar state. So let me play. So right now, right at the stopping, it has some fluctuation. And then it's slowly moving to this gray color over there. And then it stays there. So same applies to the mass fraction, the mass weighted species. Right now, it was fluctuating in the blue color. And then you can see it's slowly moving back to gray color. So I'll skip this slide. So one thing you can find out that there's some time which self-similarity doesn't work because there is a small change from the one profile to the other profile. And then when it established a new profile, we're able to derive the formula for the centerline values, both the mixture fraction and then mass species weight. So same layout. The black color is a steady state profile. The blue one is instantaneous, and dashed line is this profile. So if you look at how it fit into the model over there, so it doesn't work at the beginning because it has a transient which doesn't satisfy the self-similarity, but after some time you can see that it matches very well. So it's just simply plotting this. We find some parameter from the DNA simulation. And quite interestingly about the mass weighted species age, quite surprisingly there's no time dependency. So same apply here. This is our theoretical prediction. Coming from this color, the instantaneous value is slowly converging into the dashed line over there. So I skipped a lot of derivation, but these formula are coming from assuming the self-similar profile, assuming the self-similar of the Navier-Stokes equation. Okay. So conclusion: we investigate the stopping jet case, and then it turned out after some transient time, all profiles become self-similar. I only show the mean profiles, but also the Reynolds stratum has become self-similar as well. So mass fraction become X over T, and then mass weighted species become X, and so forth. Okay, thank you.
That's a very technical question. What's your outflow boundary condition for? So
we have a wall. We have a wall at the inlet, and then the side are kind of Navier-Stokes period. Navier-Stokes boundary condition. So there is actual entrainment coming into the jet.
And for the out?
Just a Navier-Stokes outlet.
And you have no issues with the flow exciting your computational domain?
So actually we have much bigger domains. So actually flow in the far away is very small, and then it didn't cause any problems for us.
And how do you take into account the entrainment on the sides?
So Navier-Stokes kind of take into consideration automatically. So. Yeah.
Okay, maybe follow up. Okay, move on to the last presentation. So thank you very much today.
Good morning, everyone. let me entertain you with something which sounds exotic, but I'll try to convince you that classical dynamics explains all these observations in superfluid helium in the limit of zero temperature, if you understand what we are doing. Right, I'll first give you a tutorial, and then we'll show you our kind of ideas and experimental results. It all covers about 12 years of recent developments in Manchester experimentally, and I think here we've got some progress. I'll try to convince you. Right, what is a superfluid helium? It's a fluid which can be poured into a beaker, and it has basically a zero shear molecular velocity, truly zero, but more importantly, all vorticity can only exist in the shape of singular vortex lines physically of 1 angstrom thickness. Yes, basically a turbulence is a tangle of these lines, which fortunately can reconnect and do this very frequently, which allows this tangle to evolve and decay eventually. And the reconnection processes do trigger some releasing of flow energy, well, either diffusion of vortex loops elsewhere, or generation of short wavelength Kelvin waves, which then can start producing sound and hence lose energy. So there is dissipation in this system, but not through viscosity. The interesting observable is the total length of the vortex line. It's a very well-defined quantity, and that's precisely what we watch. Unfortunately, it's called L traditionally, yeah, but it has dimensions inverse length square. Yes, it's basically the total length per unit volume, right? And but it's not enough to quantify L. You need to know how the tangle is arranged. It can be arranged purely randomly without much large-scale flow around, or there could be some alignment of vortex lines, and big edges, basically classical, because they go around many quantized quanta of circulation. You can treat them classically, and that's the approach. Basically, any tangle can, in principle, be broken into, decomposed into fully polarized and fully random components, as well, numerical experiments show. We will be using two simple continuous variables: the total vortex line density and some velocity fluctuations on the scale much larger than the typical intervortex distance, which we'll be treating absolutely classically. And vortex lines are absolutely classical objects. They obey Euler or whatever, Helmholtz dynamics. And the important tour de force, phenomenologically, we would expect that the rate of energy removal from the system is proportional to the square of the vortex line density. Whenever you try to produce any model, you end up with this formula based on dimensional grounds, where kappa is the quantum of circulation, L is the density of vortex lines, and zeta is something of order unity, dimensionless. And I'll show you then that experiments show that it's equal to 0.1 for all types of polarization, which was not quite obvious 10 years ago, because there were ideas that polarized tangles actually dissipate energy less eagerly than random tangles. I'll talk about that in a second. Just to give you an idea, what can we do? We can rotate the whole cryostat and then stop it, and it produces lots of turbulence, but unfortunately with residual vortex in the middle. Or we can tell a grid through a vortex, through a superfluid. We do that. We can do that. In this, basically, talk, I will be using something simpler. We'll be injecting a jet, precisely as in the previous talk. We can do it temporarily or for a long time, and depending on that, we can either inject very little impulse into the system or a lot of it. And that will actually be our control of how much of classical eddies we produce while already introduced a vortex tangle. So it's a control of polarization. Right, so yeah, that's basically our technique. We just produce jet of different length, duration, and just we can use the energy spectrum. And if this were purely classical system, you would expect Kolmogorov type of spectrum. We are releasing energy from the, it's a free decaying system in our experiments always, after things have settled. And the energy is decaying, kind of released from the energy-containing edges, rolling down with a constant flux, and that's it. And disappears. It was a classical fluid. But in the quantum system, it actually then enters the, well, there is another component. purely hydrodynamic energy of circulating flow around each of the vortex line. And because it basically only logarithmically depends on the distance between vortex lines, on the cutoffs, it's more or less proportional to the total length of vortex tangle. So in other words, if we know the value of L, we know how much this peak contributes of this quantum contribution, we call them, but it's a purely classical flow, kinetic energy. Or if there are some alignment of these lines, the more of it, the more of classical edges we have. And that's another degree of freedom in our experiment. Basically, we can almost independently change L and U. And I'll show you two simple examples what happens if one of them dominates over the other. For example, if the tangle is truly random, no large-scale flow at all around, then by actually telling that its energy is proportional to the length of lines and decays at rate L squared, you immediately, by equating this to that, end up with L decaying as T2 minus 1 with a prefactor which only depends on the zeta, it's the efficiency of this process, dimensionless quantity. And then the energy goes somewhere, either into sound or into diffusion to the walls. On the other hand, if we have really a dominant, very strongly structured or polarized tangle with lots of edges there, much energy sitting here compared to here, then that the Taylor hypothesis that that's the rate of the decay of the largest edges, we should equate this explicit time dependence to L squared, and immediately we are getting decay, not T2 minus 1 as before, but T2 minus 3 halves. And again, with the prefactor from which we can extract the efficiency, zeta. By the way, 10 years ago, there was quite a stir by Lvov, Nazarenko, and Rudenko, who said, because the dimensionalities of three-dimensional eddies and kind of Kelvin waves here are very different, there will be a bottleneck, a pile-up of energy will not be easily transferred from classical degrees of freedom to quantum. It was controversial, and well, at the end I will try to show you that there is no bottleneck here, at least according to our experiments. Right. Just to show, yes, and we did succeed in different works to produce either truly a random tangle which decays as T2 minus 1, or truly sort of dominantly quasi-classical tangle which decays as T2 minus 3 halves, which indicates that there is a very well-established dominant Kolmogorov spectrum of due to polarization of vortex lines. Yep. Right. What if we have now both comparable or some, what I'll do now, I'll take this formula, the energy release of the energy containing eddy of the size of the container, plus energy release from the quantized flow around each of quantized vortex line, sum them together and equate to L squared. Immediately I'll end up with a really simple differential equation which can be solved subject to, for L versus time, subject to initial conditions. And that's basically our experimental results, where we can, by introducing more or less the same density of vortex lines, actually by running our jet for different times from 2 seconds to 500 seconds in our cell, which has size of 45 millimeters cubed. We can introduce either a lot of classical flow, which would immediately decay as T2 minus 3 halves. This is log-log scale of L versus T. So all late time decays T2 minus 3 halves. Or by running it for short time, we can really start from 1 over T decay, which shows that actually a random tangle is much more dominant over very tiny classical flow. But still, at the end, because the classical eddies are decaying much, much slower always, they will actually show that they still exist, and this T2 minus 1 will always switch to T minus 3 halves. That's basically the very fresh result that now we can, well, basically explain the behavior of when both classical and what we call quantum flows coexist. But the important thing that for both types of for all types of flow, we use only one this effective parameter zeta, and it, as you can see, solid lines describe the experimental observations reasonably well. And that's the conclusions. We understand what's happening well, hopefully, we have control of the experiment, and we also have a control of our model, which is quite satisfactory. So just a single parameter is required for any polarization. So worries that there should be bottleneck between two different cascades are probably unnecessary. Thank you very much.
So there isn't a pilot, but there is a flattening of the spectrum.
Well, nobody knows what's happening in between because it's a murky region. Yeah, you can't. I mean, both sort of simple approaches fail. Yeah, but fortunately, if we have really a large scale separation, the dominant parts sit far away from this kind of intermediate region about which we know really little. Yeah. But at least it seems it's working quite efficiently by sort of milling these large edges into whatever, small vortex rings or Kelvin waves or phonons, sound.
There's a quick question. Thank you.
There's a couple of different types of dissipation for the quantum turbulence. Does the balance of that matter, or does it change for different conditions?
Well, you see, for this zero temperature limit, it's all very speculative. Nobody has yet actually pinpoint any of these. We don't know which mechanism is dominant. I showed that it could be vortex loops, which could have a very small and fast, which will go away to the walls. Or it could be sound emission by a very high frequency Kelvin waves after the incompressibility assumption breaks down. We don't know. But it seems phenomenological, all of them should kind of be described by this L squared dependence. So experimentally we observe the prefactor. Yes, it would be nice now to go into visualization and actually try to see who is the culprit, and that's what we're going to do next year.
Okay, thank you very much. Thank you.